I am Yuvraj, a PhD student in Building Technology Construction Management Division. So today I'll try to briefly give you some glimpse about limestone calcined clay cement, which is a new composite cementitious material which has been studied across the globe. And in line with the mineral admixtures lecture which we have been listening so far in the course, I'll also talk about how limestone and calcined clay as a combination can work as a very ideal mineral admixture. Right? So most of you are aware by now, there is a Portland pozzolana cement, which is composed of clinker and fly ash. So mainly you use some amount of supplementary material like fly ash or slag to create a blended cement. One of the cement is common cement, which is widely used in India, is PPC. Its composition is made up of clinker, around 25 to 35% of fly ash, and also gypsum. So when you look at LC3, the composition is you have clinker, which is obviously the major component which is reacting and contributing to the property. Then you have calcined clay, which is a pozzolan per se, and we'll discuss more about clay and its pozzolanicity. And you have limestone. So you need to understand the difference here is instead of burning the limestone to produce clinker, you are adding the limestone directly into LC3. So in this way, we are able to get better utilization of the material, right? So you don't burn the limestone, which means calcium carbonate. When you burn, it leads to carbon dioxide emission. So instead, you directly add this material. So by going for this combination, we are able to bring down the clinker content to about 50%, right? Without any compromise on the property. So in general, what LC3 is a ternary blended cement. So instead of just having one material to replace your clinker, you are replacing it by parts with limestone as well as calcined clay. So it's made up of clinker, calcined clay, and limestone. Alternatively, when you just use a combination of limestone and calcined clay and add it just like a pozzolan, like your fly ash, silica fume, or metakaolin, so this combination of mineral admixtures is called LC2. So there are some unique benefits which we can get by going for such combinations. So in the first place, what we need to understand is, so for example, when you have a plain Portland cement, let's consider these are the clinker phases, and when you add some amount of water to the cement, you have the water which is spread between the clinker particles, right? And over the period of hydration time, this entire interparticle space or the capillary pore space will get filled with hydrates. What happens is when you have some amount of SCM which is added to the mixture, so for instance, the red particle which you see here, it can be fly ash, slag, or clay. So these will contribute to the space filling. Instead, what happens is these spaces will be filled by reaction from these material. And when you move to ternary cements, you are removing even more some amount of clinker and replacing it with limestone. So when you go from cement to SCM and to limestone, what happens is the reactivity of the material, which is how much reacts in water at what pace, that keeps going down. So clinker is the most reactive component, and next would be your SCM, and limestone is not generally reactive. Additionally, what happens is because of this, the demand to fill the space between the cement particle or the SCM to cement particle also improves, right? So there is more demand, so you need to more effectively fill the space which is filled initially by water with more amount of hydration products. So let's look at how this happens in terms of basic reactions. So when you take a plain OPC, which you can see the hydration products over the period of time here. So initially you have some amount of ettringite which is formed, and later it comes down, and which is followed by the formation of monosulfate. And CSH and calcium hydroxide are the main hydration products which are formed, right? So when you start moving from OPC to an OPC plus SCM system, so what most of you are aware, this SCM will react with calcium hydroxide. So instead of the trajectory which is presented here, the calcium hydroxide will start reducing after some point in time. This in turn will lead to increase in some amount of pozzolanic CSH, right? So there is more amount of CSH which is formed, which start contributing to properties more slowly, right? When you replace OPC with just limestone, interestingly, what happens is this blue curve which you see here, which is the ettringite which is formed initially, it doesn't come down. So instead, the ettringite will remain stable, right? So you don't have the ettringite coming down, because when you have limestone, the ettringite amount will be prevented to convert to monosulfate. Instead, you start forming some hydrated phases, which I'll explain. These are called carboaluminate phases, formed by reaction of limestone with the clinker phases, right? So when you combine these two reactions and form a ternary binder where you have OPCs to some amount, SCM and limestone, so you have a combination of both these reactions. You have the regular CSH forming from clinker, you have the ettringite which is formed and prevented from conversion. I have given a lighter shade to show that in ideal case it will happen, but in this combination it will not happen. So ettringite will remain stable, right? And then you start forming these carboaluminate phases from limestone. In addition, because of SCM, you also have calcium hydroxide reducing and pozzolanic CSH increasing. So let's take a deeper look on what really happens because of this, right? So these phases are again contributing to filling of the capillary space. So you have ettringite which is stable and carboaluminates forming, and the additional two reactions. So you have reaction of clinker which will get accelerated because you have less clinker and it's reacting to a more amount of water which is present. You have ettringite which is having lower density. So density of ettringite is 1.6 compared to CSH which is around 2.2, which means the phase which has lower density will have more volume, right? So this ettringite which is stable will rapidly contribute to reduction in porosity because of the density differences. And then you have increase in carboaluminate phases and lowered portlandite and formation of pozzolanic CSH. So you have a combination of all these 5 reactions which happens over the period of time, providing some kind of synergy to the reduction in porosity. So as we all understand, when you are able to reduce the porosity, you will drastically improve properties both in terms of your strength as well as durability, right? So we'll look at that. So essentially you need to understand that there are these different reactions which happens when you start moving from a regular blended cement to a ternary cement with limestone and SCM, right? So to summarize, so you have this initial space, it gets filled with hydrates. So basically when you replace with SCM, you have 2 reactions, which is portlandite consumption, calcium hydroxide, which leads to formation of CSH and CaSH. And then you replace some more amount of clinker, right? So when you replace some more amount of clinker, you need to fill this space much more rapidly. So you have the acceleration of clinker, stabilization of ettringite, and increase in carboaluminate phases. So you have 5 different reactions which are happening parallelly when you have a combination of limestone calcined clay kind of binders, right? So let's look at the basic reaction. So this is a ternary phase diagram of cement hydrate phases, not really the elements, right? So you have pure calcium, which means you can have calcium hydroxide or limestone. In pure silica, it can be silica gel, silica fume, right? And then you have regular SCMs, which can be natural pozzolan, fly ash, metakaolin, right? And then the hydration products will have a range typically around this region, right? So when you consider pozzolanic reactions, what happens is because you add more amount of silica to your Portland cement, the composition of the silica will contribute to reducing the composition. So the alumina from the SCM and silica from the SCM will react with calcium hydroxide and forms CaSH or CSH. Why you have CaSH? Because some SCMs, for example, metakaolin or slag, can have alumina in it. So when you have alumina, both silica and alumina will react. So you form CSH along with alumina in it, which becomes CaSH. When you have limestone, what happens is, so you add something in this region, right? And this is reacting with alumina, which is coming from clay, which is metakaolin. And finally, what we form is a hydration product, which have a chemical formulation on around this region. So which are called AFM phases, right? Which are carboaluminate phases. So these have some amount of calcium aluminate, calcium carbonate, as well as water. Interestingly, what happens is, depending on the kind of SCMs which you choose to use, for example, if you use a fly ash or clay in LC3, the rate at which your CSH get formed is different, right? So your fly ash, for instance, I have given a cartoon as a representation, so most of you can remember, it dissolves much slowly like a temple, right? So it contributes to development of property much more slowly, right? Whereas when you have calcined clay, right, clay is much more reactive. So the tendency to form CSH is much more rapid in LC3. So this reaction, which is expected to happen, it happens much faster in the case of limestone calcined clay cement, right? So moving forward, I will talk about different components which is present in the limestone calcined clay cement. So firstly, clay. So when you look at clay, so most of you would be aware that there are different types of clay. So you have kaolinite clay, illite clay, montmorillonite clay. So I have given a schematic representation of different clay structures. So what you have is kaolinite is a form of clay which is 1:1 clay, it's called, and the other forms of clay are 2:1 clay, right? So when you have 1:1 clay, what it indicates is you have equal amount of alumina and silica. So for example, if you see this crystal structure diagram, you have a silicate sheet and gypsite, right? So gypsite is nothing but aluminum hydroxide, right? So when you have one layer of silica sheet and one layer of gypsite, which means you have silica and alumina in equal amount, right? Moving from kaolinite, the other forms of clay, which are 2:1 clay, for example, illite or montmorillonite, right? It will have one gypsite sheet attached to two silica sheets, right? Additionally, there is a cation, which is potassium in the case of illite, and in the case of montmorillonite, it can be calcium or potassium. So these will bridge the silicate sheet. So you have effectively lesser amount of alumina in the other two clays. So the essential point is, initially the clay, which is naturally present, will have a proper crystal structure. So these are crystalline phases, right? So to make it react in cement, what you need to do is heat treatment, right? So when we say heat treatment, what it means is you put the clay in a furnace, right, and heat it at around 600 degrees Celsius theoretically, right? So when you heat it, these proper sheets get broken. The hydroxyl ion, which is bridging from the gypsite to the silica, it gets broken. So when it gets broken, then it forms an amorphous structure, right? So I have given a representation here using a technique called X-ray diffraction, right? The nature of crystalline phases present in your material. So the black line here indicates the rock clay. So you can see some peaks which are shown here marked as K, right? Those are kaolinite peaks. The faces corresponding to kaolinite, right? So when you heat it, so this red line which is in the bottom, it's a calcined clay where we have heated it to around 800 degrees Celsius and then did the same experiment. So when you do it, you don't see the same peak in the two regions which are marked as kaolinite, which means this organized crystal structure is being broken and it has now formed an amorphous, a disordered structure. So when it forms a disordered structure, and then it can potentially react in your cement, right? So the kaolinite phases decompose at around 600 degrees Celsius theoretically, but when you do a large scale, typically you need to calcine it at 800 degrees Celsius to make sure uniformly the clay is decomposing, right? Decomposition of kaolinite peak indicates that the clay has been calcined properly. You don't want to have an uncalcined clay, because clay, as we all know, sometimes some other forms of clay impurities can absorb water in it. So you don't want these crystalline phases present in your cement system. So you need to remove these crystalline phases and make it amorphous, right? And also I want to point out there are some other phases which are marked as Q. So these Q are nothing but quartz. Quartz is a crystalline form of silicon oxide which is not reactive, right? So the quartz phase will be present both in your raw clay as well as processed clay. We are not going to disturb that. So we are worried mainly about calcining this kaolinite, which is a clay phase, right? And most importantly, you need to remember, out of the three clay, kaolinite clay gives equal amount of silica and alumina because of the nature of its crystal structure. Whereas when you use other two forms of clay, you are going to have lesser amount of alumina, right? Let's look at a clay, like what are all present in the clay when you look in a microscope. So this is one of the kaolinite clay which we have put under a microscope and try to look at the different phases. So, and then what we did was we color coded the different element, right? So this was done using an experiment called elemental analysis. So what you can see is there are these major elements which are present. You have aluminum, you have calcium, which is very minor amount, and then you have iron, you have silica and titanium. So let's look at which of these phases are present in what forms, like what kind of formulations. So when you see a bright green spot here in the silica, and you can see the structure, it's not a porous or a disordered. This is a quartz phase, and I have told you already that a quartz phase is not going to be reactive. So we have some amount of this quartz, right? And then you can see some bright spots in the iron region, right? Which means you have iron in your clay. So in general, the clay which we use in LC3 is reddish in color. So one major reason why this reddish tone comes to the clay is because of the iron impurities which is present, right? So another important characteristics is we can use this clay which has slight reddish color in it in cement systems, right? Because we are not worried about the cement color of the cement as much, right? Whereas these impure clay, if it is not used in cement, it will not be used in other major industries. For example, clay is also used in other products such as paint, ceramics, where they want a purer form of clay. They will not be able to treat this iron. So the iron which is present in the calcined clay is not going to react, but we are not really worried about it, right? The major focus here is to study how much of these reactive phases are present. So the region where you see bright red spots combined with the green spots, those are the alumina and silica rich amorphous phase. So which when you backwork to the actual microscope image, you can see this glassy phases which is present, not really the crystalline phases. Those are the phases or the amount which will react with your cement. And you can very well see we have a lot more of these phases in the clay compared to the crystalline phases of iron or silica quartz, right? why this is important. Like, so here in this slide, I have tried to present different compressive strength evolution of cement mortars made with different forms of clay. So these are the strength development for the plain Portland cement. So you can see strength rising from 1 day to 90 days, right? When you replace cement with just something which is inert, right? It's a filler, nothing going to react for about 30%, right? The strength are being reduced as expected because you are replacing with something which is not going to react, right? Whereas when you add K600, which is a kaolinite clay treated at 600 degrees Celsius, you can see that strength from 7 days, it's being brought to about similar range like your plain Portland cement, which shows that the kaolinite clay is reacting, contributing to this reduction in porosity, which I talked about initially, and leading to this major rise in strength. Whereas when you look at the strength development from illite or montmorillonite clay, it's almost similar to the filler, which means these two clay, even when you heat treat it, it's not going to be as reactive as a kaolinite clay. So this shows us that when you want to use a kaolinite, when you want to use a calcined clay, you should choose a kaolinite form of clay to be used in formulations such as limestone calcined clay cement. Why this happens is because if you go back to the crystal structure of the clay, so it's easier to remove the hydroxyl ions bridging the gypsite and silica, right? Whereas the presence of cation between the silicate sheet, both in the case of illite and montmorillonite, gives some sort of stability or preventing the clay from reacting even though you heat treat it, right? So this difference we should understand and make sure we are picking the right form of clay to be used in the cementitious system. Coming to limestone calcined clay combinations, what happens is we know that kaolinite clay is reacting. The next point is to understand what forms of kaolinite clay I should use or how much pure should the clay be. So in this graph, what I have shown from one of the literature is kaolinite clay content versus strength, right, at different ages. So for example, this line indicates strength development at 1 day for mortars made with clay of different kaolinite content. So if you have 100% kaolinite content, this is the strength. If you have 20% kaolinite content. So what we mean by kaolinite content is the remaining amount can be quartz. So when you take a mark, for instance, 40% of the 100-gram clay is reacting, and remaining 60% is the crystalline phase which I have shown you before, right? It can be in the form of quartz as well, right? So when you look at the strength development, you can see that the strength is directly proportional to the purity of clay, right? When you have higher kaolinite content, you get better strength, which is quite obvious. So additionally, what the literature has done is the authors have done is they have tried to mark with black lines the strength of ordinary Portland cement when you don't have any clay. So interestingly, what you need to see is by 7 days, if you have just 40% purity in your clay, it can have similar strength to your OPC. So for example, when you choose a clay which is only around 40 to 50% purity, it can produce similar strength to your OPC, which shows that you don't necessarily have to use a high purity clay, which is very difficult to get and which has better utility in the other industry. You can use the clay which is not so pure and still get similar strength like your OPC. Additionally, another observation which they made was when you go for clay which is much purer than 50%, you are not going to increase the strength at later ages. So you can see the dark green points here, which is 90-day strength. Initially it rises and then it sort of flattens out, which means when you just use a much purer clay, you are not going to increase the strength any much. So if it's not going to contribute to properties, why we have to use a much purer form of clay? So currently, the premise is in a combination like limestone calcined clay cement, which is optimized for clinker content, energy efficient material utilization. So we are recommending to use a clay which is containing only 40 to 60% kaolinite content. So these impure clays can be used in combinations to produce similar properties like your OPC. So this is with respect to your clay. Let's look at what limestone is doing in the system. So essentially, to give a background, limestone is nothing but calcium carbonate, right? It is one of the most widely available material, which comprises around 4% of earth crust, right? It can be present in other forms as well. For example, your chalk is made of calcium carbonate, marble dust in some is made up of calcium carbonate, or marble, which is deposition of sedimentation, which is made of calcium carbonate. Even in the paper production, the sludge which is made of paper that can also have calcium carbonate. And there are deposits locally available in different region, which is called marl, which is a mixture of clay and calcium carbonate, right? And additionally, nowadays people are looking at making calcium carbonate by means of artificially carbon sequencing carbon dioxide into calcium or magnesium. So when you mix calcium carbon dioxide in the atmosphere with any of these cations, you will form calcium carbonate. So there are different forms which is present. So in the image, I have shown one of the deposits in the cement plants, right? Ariyalu in Tamil Nadu, right? So these are the deposits of limestone which is available. Why it's finding lot of interest to be used in cement is because you have to transport fly ash from one region, bring it to a cement plant, and then produce a blended cement. But when you can make an opportunity available by using limestone directly in cement, it's available near the cement plant. So all you need to do is you just take the limestone, grind it, and directly use it in your cement, right? And cement plants already have facility to use the limestone because they have been taking these limestone, then burning it to produce cement for their processes. So definitely they just take the limestone directly as such and grind it and use it in cement. So, but what does limestone does in cement? So, for example, here I have given one of the transmission electron microscope image. So, which is a higher version of a secondary electron microscope. So, you can see the scale here. It's about 500 nanometers. So, we are looking at nanoscale reactions. So, the two dark black region which you see here, these are C3S grade. So when you mix with water, obviously your clinker phases produces CSH, which is around this region, right? You can see. Interestingly, what happens is when you have limestone, because it has calcium, the surfaces of calcium acts as a region for nucleation of your CSH. So what happens is on top of your limestone as well, limestone grains, you start precipitating CSH initially, right? So similar to your C3S, your limestone will also form CSH on its surface. So what it does is it leads to heterogeneous nucleation along the capillary region. So for example, the interparticle region you can see here, if only cement grains are reacting, you will have CSH forming from here and bridging the region. Now that CSH is precipitating locally on limestone as well, the region get bridged much faster, right? So this is one major reason why limestone is getting a lot of attention, right? There are other chemical effects as well. So what I discussed is one of the physical effects. So let's try to look at what all limestone brings into an hydrating cementitious system, right? So it has two major roles. One is I am classifying it as a physical effect. The other part can be classified as a chemical effect. So in physical effect, basically, it's called the filler action, where you have three major components. One is dilution. Dilution means you are reacting or you are substituting clinker with something which is not so reacting, which means you are diluting your hydration product. The amount of hydration product which is present will be lower because limestone does not react as much as a clinker. The second effect is called a shearing action. Shearing action is because when you have a limestone particle which is not reacting, when you mix cement, it will shear and create lot of sites on your clinker grain where reaction can happen much faster, right? The third component is reducing interparticle space. This is quite interesting because what happens is the limestone is much softer compared to clinker. Because it's softer, when you grind it to clinker by means of grinding process, the limestone get ground to very fine particle sizes. Because it's finer, it can pack better between the clinker grain. So it improves the packing in a way, right? So this reduces the pore space which I initially talked about, which need to be filled with the hydrates, right? Then chemically, when you dissociate limestone, you have calcium ions and you have carbonate ions. Because of the calcium ions, the nucleation of CSH tends to happen on calcite surfaces. This leads to acceleration of C3S reaction. So what happens is, because CSH is forming elsewhere on limestone grains, the amount of CSH formed on the surfaces of C3S also improves, because of which the C3S reaction, which is tricalcium silicate, the major clinker illite phase, the reaction of the C3S also improves. Then you have carbonate ion. So what carbonate does is, as I talked about initially, it stabilizes ytringite, right? And then the carbonate react with alumina, which is present from clay, right? Calcined clay, as I told, it composed of silica and alumina. So the carbonate react with alumina to form hydrated phases, which are called as monocarboaluminate or hemicarboaluminate, right? You can go back to the initial slides and check the equations for these phases. Additionally, the carbonate will also get absorbed on the CSH, right? So some of these anions, carbonate ions, will get adsorbed on the surfaces of CSH. So CSH is an amorphous, not really a pure crystal irregular structure. So it can bind a lot of these additional ions on its surfaces, right? So you have a range of different reaction happening in the because of the limestone present in your system, right? To classify what happens is, so this is a heat flow diagram, right? So the black line corresponds to OPC. So when cement reacts, it's an exothermic reaction, right? So there is a heat release which happens. So when you have just OPC, this is the heat release curve. So initially, lot of cement is reacting. Later, very minor amount will react post 1 or 2 days, right? About 50 to 60% reacts in the first 2 days itself. So this is a heat release. When you replace with 30% fly ash or 45% fly ash, the red and pink line. So you can see the heat release curve just reduces proportionately, because fly ash can react only after 7 or 14 days in your, even after 28 days in some instance in your cementitious system, right? So because of which the heat release rate is reduced. Interestingly, when you add limestone, so for example, along with 30% fly ash, I am adding 10% limestone to it. So when you add limestone, what happens is the heat release rate gets shifted this way, which shows the nucleation effect which I was talking about. So because it's nucleating, it's enhancing the reaction of clinker, the heat release rate is being shifted, which means you are accelerating your setting process, you are increasing the reaction which is happening at early ages. So when you use a combination of limestone in your cement, it can contribute to early age properties, right? Even with 15% limestone, you can see the curve is shifted, right? Whereas when you just increase fly ash content, you are not going to shift this reaction curve, right? So because this some interesting aspect of this reaction is, so for example, because the reaction is slowing down with replacement of fly ash, your setting time of fly ash is sometimes problematic. The concrete may not set at an ideal time when you have high volume fly ash, right? So this can be compensated by adding limestone to your cement, right? So the physical and chemical effect, the two parts which I talked about, can be classified as when it happens in your reaction. So for example, the nucleation effects, which leads to formation of CSH, it will happen during the early ages, which is during the main hydration peak. The chemical effects, which is your pozzolanic CSH or formation of carboaluminate phases, all this will happen in the later ages, post your main hydration peaks, right? So this difference we need to understand in terms of what limestone brings in to your reaction hydration process, right? So why go for a combination of this calcined clay and limestone? So what it's going to do? So here I am presenting some strength development of limestone calcined clay combination. So the black line indicates strength of OPC. The gray parts are strength of just calcined clay, for 30% or 42% calcined clay, right? The green bars indicates calcined clay limestone combinations. So what happens is when you increase calcined clay limestone combination in terms of early strength, you can see optimally at around 15% limestone, you have similar strength to your calcined clay, just calcined clay system. More interestingly, at later ages, for example, long-term strength, at 180 day, this is for 30% calcined clay. When you increase just calcined clay, right, the strength reduces because you have consumed all the calcium hydroxide which is present. So this sort of plateaus the reaction. The reaction never happens after that, right? Because you need calcium hydroxide for your pozzolanic reaction. Now, when you replace this calcined, some of this calcined clay amount in this 42% calcined clay mixture with limestone, because limestone does not require calcium hydroxide to react, it's going to produce other benefits. You can increase your strength, which is similar to your OPC or even equivalent to your 30% calcined clay system. So by going for this combination, we are able to extend the benefit, right? Why this happens? If we start looking at the phase diagram, what really happens is when you have a combination of this hemicarboaluminate and monocarboaluminate phases, so which is at this reaction, right? So the limestone brings in carbonate ions, the clay brings in aluminate ions. So the x-axis here indicates increase in the amount of carbonate to aluminate ions. When you have more amount of carbonate corresponding to aluminate, you form hemicarboaluminate. When you have the value increases, it forms monocarboaluminate, right? AFT is the ettringite phase. And you can see portlandite, which is more or less stable across this region. Interestingly, because of the density difference which I talked about, these phases have a lower density corresponding to your other phase. These, when you look at the volume proportion, they have a local maxima in terms of your solid volume, or else it is a local minima point which respect to your porosity, right? So when you have an optimal combination of carbonate to aluminate, which but chemically or in the practical scenario, it's more like a ratio of calcined clay to limestone, then you have higher amount of solid volume, which is volume of your hydration products, which will produce minimum porosity in your matrix. And when you have minimum porosity, you obviously have higher strength or durability in your mixtures. So this is the science behind going for a combination of calcined clay and limestone in your limestone calcined clay cement. So that's how the new formulation of limestone calcined clay cement works, right? So it has a pretty strong scientific basis on how this combination of chemical reaction would contribute to properties. Going forward, let's understand, like now we know that the reaction which is happening and what is a scientific basis. Let's look at some realistic data when you make concrete, whether it's going to work in the similar fashion. So what we did was, these are study done by one of my colleague here in our lab. So we did different types of concrete. So an M30 grade concrete, M50 grade concrete, right? So because of this synergy or the reaction between all three components, so OPC is plain Portland cement, fly ash is fly ash cement replaced with 30% fly ash, and LC3 is the new combination. You can see OPC and LC3 as almost similar strength development, even higher in some cases at later ages, both in a lower grade concrete as well as in a higher grade concrete. Whereas in the case of fly ash, your strength rises much slowly and ultimately it reaches similar point, right? So higher rate of strength development would mean that you can even cure this concrete less. So one problem in construction is, when you adopt a blended cement, you have to cure it for longer time. And we know that it's difficult in a construction site to cure it for longer time, right? So when you go for this more optimized combination, like an LC3 binder, it can have similar strength development like your OPC, right? This is one major benefit which we can attain by using LC3. On this side, I have shown the strength development of concretes which has similar combinations, which means same amount of cement in it, same amount of aggregate, and same amount of water, right? When you have everything same, you don't change the mix design for strength. Even then, limestone calcined clay cement produces higher strength than most of the common cement which are used in current construction practice. It can be plain Portland cement, it can be a fly ash cement, right? So when you start making concrete, we can see that we can really extract some benefits out of this new combination of limestone calcined clay, right? These are with respect to strength. So another aspect we need to understand is, yes, how much of this strength happens at which duration. So for example, here I have given strength of cement paste, right? Whether when you make systems with different water binder ratio, we'll have same kind of strength development, right? So this is for fly ash. Fly ash reacts slowly. So what happens is, I've given strength development for different ages. So this is for 1 day, 3 days, 7, 28, up to 90. You can see the major shift in strength happens between 7 to 28 days, right? Across water binder ratio, whether you have 0.5 water, 0.4 water, or 0.3 water, lesser water in your cement. The major jump in strength happens between 7 to 28 days, right? Obviously, when you have lower water binder ratio, strength rises in some extent here as well. But in LC3, the major strength development happens between 3 to 7 days, right? In cement paste, which means the binder itself has a higher potential to attain strength at an early age, right? So that's why we see a major strength rising at the early ages, right? So let's talk about other implications of such binder combinations, like for instance, durability, right? So when you have a chloride attack, right? So the chloride moves into concrete. So for instance, when you make concrete system, the chloride moves into concrete, reaches the surface of steel. So for example, this is the surface of steel, and it can lead to corrosion, right? So when you use a LC3 combination, I have presented here chloride content versus depth. You expose it to chloride and measure how much of chloride has moved at two different depths, right? So when this is for the OPC concrete, you can see higher amount of chloride which has moved even up to 20 millimeter, right? When you use fly ash, the chloride content is lesser. It has reached, for instance, example, around 10 millimeter. But in the case of calcined clay, the chloride content has reached only 5 millimeter, right? So which shows there is a lesser amount of chloride which is moving inside your concrete in this combination, right? And when you expose time, then it's going to take a longer time to reach the surface of steel, right? If you have cover depth of 50 millimeter, it will take a longer time, right? So when you can obtain the rate from this curve. So here I have presented the rate, but you can it's in terms of millimeters square per second. So you can understand 10 times compared to OPC, which means chlorides are going to move inside your concretes at a rate 10 times lower compared to OPC in the case of your LC3 concretes, right? Another aspect we saw was all this multiple reaction happening at a very early age. So whether curing would be a problem. So here I have presented the chloride movement rate, which is migration coefficient, versus curing age, which means you cure the concrete only for 3 days and then don't cure it, right? And then cure the concrete only for 7 days. Don't cure it up to 28 days, and steady was done at 28 days. And third case is when you cure the concrete completely for 28 days, right? And then do the steady. So when you take all these 3 cases and then do the steady at 28 days, so you can see in OPC, the value is almost similar, right? In fly ash, there is some effect, right? If you start curing, so this is for fly ash, compared to 3 days, 7-day cured concrete perform better at 28 days. Compared to 7-day, 28-day concrete performs even better. And when you extend to 56 days, it will perform even better than this, right? In the case of LC3 combination, the value is always nearly 10 times lower, right? Because all the reactions are happening much faster, right? And the porosity is reduced at a very early age, irrespective of whether you cure for 23 days, 7 days, or 28 days, you will have a very slow rate of movement of chloride inside your concrete, right? So this is something which we want, right? When you make a bridge out of the concrete, you want to make sure that there is lesser amount of these chemicals which move inside concrete and lead to deterioration. The another benefit by optimizing the combinations which can attain lower porosity and pore sizes is you can attain much better durability at early age, right? So this is another benefit which we can extract in the limestone calcined clay cement combination, which is lesser dependency on curing, right? So to make industry adapt, we did a range of field studies. So when you get back to industry after the coronavirus stuff, most of you should pass through the road in front of chemical engineering department. So a new chemical department, right? So we have made a payment out of LC3. When you go ride with your cycle, you should see the color difference, right? We have a part of the payment made with OPC and part of the payment made with LC3. And we have seen that over the period of service, we made it in around 2016. Now it's 4 years. It's kind of rigid, and there is not much difference because it's a new combination and the chemistry of the binder is different. We did some field kind of studies. So you can go and check out the payment. We did some RC slabs, which is similar. Like when you go look at the construction site, it will have reinforcement, right? So we made similar slab and check the chloride diffusion rate, right? So, and we cured it similar like how an improper construction practice will cure. They'll just put a gunny bag over the concrete and cure it for only 14 days, leave it open in a sunny condition. We did it in similar way, and we found the difference between field and lab specific, right? Because make a much different to LC3 in terms of chloride rate. And another field demonstration which we did was in an army site in Leh. So this is a payment for army truck to come and rest. It's an heavy duty payment made with air content. So it's made of M35 grade, and what we plan to do is after a winter cycle in Leh, we wanted to go back and see whether the LC3 cement or the concrete made with LC3 cement is going to be integrity of the payment is proper after this cycle. So these are some field demonstration which IIT Madras has attempted to do over the period of this years. Obviously, when you have new cement, to make it acceptable in the industry, you have to do a lot of research. So right, so there are lot of other things which are happening at IIT in our lab. So when you do an internship or something in the lab, you will see there are works happening in the new cement combination on carbonation, sulfate attack, corrosion of steel, creep and shrinkage, whether workability and rheology can be controlled in the new combinations. So these are some of the works in progress. And finally, I would like to conclude by showing you some links to references. So you can read more about the LC3 project in this web link. There is also a lecture by Professor Gettu, which is available on YouTube on the work done at IIT Madras. Other references which shows what is basically LC3 is. And with this, I will conclude. And if you have any questions, I'll be happy to answer. And thank you.
Thank you, Yuvraj. There are some comments which have come in the chat. Yeah. One is the question of when you have the graphs, like for the compression strength, you are showing bars. So the question was, are these bars showing the variability? Is this standard deviation or?
Yeah, so the bars are showing the variability of a number of samples, right? So you can't test one cube. So basically we test 3 or 6 cubes. So those show the difference between the samples.
Another question is, does the cost of the clay increase with the kaolinite content? Like if you had very high kaolinite content, would the cost of the clay increase?
Yeah, the more than cost of the clay, the high purity clay as application in more niche of applications such as paints where they can process it, or to make ceramics. So those clays are not necessarily available for use in something like a cement, which you need to make available at a very lower cost. So it has a much more niche utilization. So those clay goes into other region. The impure clay will be just available at the overlay. Nobody would use it in other industry. So the availability and usage of this clay is much more useful in the cement-like application.
So indirectly, it might be more expensive. But again, what you have said is it is not necessary to go for clays with very high purity. It looks like if you have kaolinite content of 50 to 60%, that is working better than the other cases.
Exactly.
Any other questions? Okay, so I think this lecture had a lot of information. This is summarizing the research done at IIT Madras and elsewhere for the past 5 or 6 years. So you can go through it again. I'll have the video posted so you can go through it. And this is a good application of a new mineral admixture or a combination of materials that are already known to us in concrete to help concrete become better and also more eco-friendly. Okay. Thank you again, Yuvraj.
Yeah, thank you, sir.